Hi everyone. In this video, we're going to talk about the normal distribution, or at least we're going to begin to talk about it. Now, the normal distribution is one of the most important distributions that we're going to see, probably the most, in all of probability and statistics, and that's for a number of reasons. One of them is because that many situations that we encounter in real life can be well modeled or well approximated by a normal curve, which means things generally look like a normal curve. And so you can think of SAT scores are often modeled using a normal curve. IQ scores often modeled using a normal curve. And so we'll get to what we mean by a normal curve in just a second. But and there are many other things, not just like standardized tests that are well modeled by something that is normal. Okay, and even sort of more importantly for us in the statistics half of this course, which is coming up fairly soon, is that even when variables don't follow a normal distribution, there's a very powerful result or theorem in statistics that says that even if variables don't look like a normal distribution or aren't well approximated or modeled by a normal distribution, that sums or averages, means of those variables, actually do follow a normal distribution. And so the important thing is called a central limit theorem. And so we'll see that in a couple of weeks, not too long. But it turns out that the normal distribution models a lot of stuff well. And so what does the normal distribution look like, or rather, what's its form? And so it has two parameters, so two things that make a normal distribution what it is. It's, that sort of thing that I've been saying a lot. The first parameter is mu, which is the mean of the distribution. And so, and the second parameter is sigma or sigma squared. So some people use just sigma, other sigma squared. Sigma is the standard deviation, and sigma squared is the variance. Now you'll notice this is probably similar to what we've seen before, because we generally denote the mean of a random variable as mu and the variance as sigma squared. And so it means here the same thing. It turns out that the mean, its parameters, one thing is the mean, the other is the variance. And so you don't actually have to calculate that, or there's no formula, sort of, it just is the parameters. It's what you give to a normal distribution to make it sort of what it is. And so you denote the normal distribution like this. So we have a random variable x. It has a normal distribution, so we use n, capital N, for what to denote it, and then it's always the mean first, then the variance. And there's no one situation that usually is the normal distribution. So x can be really counting or specifying anything. There's no sort of restrictions on what the random variable x is looking at. And the PDF of the normal distribution, so what makes that curve, is this. And so that's actually sort of long compared to what we're usually used to, 1 over the square root of 2 pi sigma squared, and then e, the mathematical constant, raised to the negative x minus mu squared over 2 sigma squared. Okay, so that's the PDF. That's what makes the curve be the curve. And an important thing about the normal distribution is that our random variable x can take on any value from negative infinity to infinity. Okay, so it's not restricted to just non-negative numbers or positive numbers or negative numbers. It is can be the whole real number line. Okay, so any value, any real value x can be taken on, or x, the random variable can see that. So what does a normal distribution look like visually? Well, it looks like this. So many people call it the bell curve. We won't usually refer to that in here, but you may have heard of the sort of the bell curve, and that's this. It's what a normal distribution looks like. The uh, mu is a position parameter or a location parameter. It tells you where the hump in the bell curve lies. Okay, and so we have two examples here on the left, a mean of 80 and a standard deviation of 15, and then a mean of 100, standard deviation 5. The first part, mu, is a location parameter. It tells you where the hump is. Okay, and so it'll be centered there. You'll see in the black curve, it's centered at 80. The blue dotted curve or lined, a curve there is centered at 100. And then the second parameter, either the standard deviation or variance, it is a scale parameter, and it controls how sort of high or low the hump is. And so you'll see as the standard deviation gets larger, the distribution gets more spread out. And so you'll see the 80 and 15 normal distribution, mean of 80, standard deviation of 15, is much more spread out than mean of 100, standard deviation of 5. That's due only to the standard deviation. And over on the right, so lower standard deviation means a higher peak. Okay, things aren't as spread out, meaning the values that you'll see from that normal distribution are going to be highly centered around the mean value, and there's not going to be a lot of variation in them. The higher the scale parameter, the higher the variance, the more variability there is. And generally, so as a general rule for the normal distribution, over on the right, you'll see that if you take the mean and then you add one standard deviation to it, you're going to get probably halfway down the curve. So if you look at the part B on the right, you'll see that the mean plus a standard deviation is going to get about halfway down that curve. And that's true for really any normal distribution. There are more specific rules that I will tell you later on. But the normal, people have studied the normal distribution a lot. And so we know a lot about it. All right. Now, basically, that's all we need to calculate probability distributions. With Minitab at our disposal, doing stuff that we usually do with probability distributions is no different with the normal distribution. Okay, but before statistical software was available to everyone, before it was available at all, people used the normal distribution a lot. It's the most popular and also, in a sense, the most studied. Okay, there are most facts about it, in a sense. And so I'm going to show you some of those facts because they're important in what we're going to do later on in the course, even though we have all the sort of tools that we need to find probabilities. And so one thing about a normal distribution is that there's one very special normal distribution, and it's called the standard normal distribution. So it's the standard normal distribution. And the standard normal distribution has a mean of 0, so it's centered at 0 and has a standard deviation of 1. Okay, and so the formula for the PDF simplifies to this, and we denote a standard normal distribution not as a random variable that has x, so it's not the random variable x, but when we have a standard normal distribution, we denote that random variable z. So usually we use x and y for general random variables, but one that has a standard normal distribution always has z as its random variable. Okay, and so whenever you see z throughout the book, it's usually going to mean that you're dealing with a standard normal distribution. And why is this important, or why is it special? Well, it turns out the property of normal distributions overall is that you can turn any other normal distribution into a standard normal distribution. Okay, so there's this sort of duality. Maybe not duality is not the right word, but there's a correspondence between a general normal distribution, say mean 100, standard deviation 5, like we saw before, and 0, 1. And the book, and many people call this a reference distribution. And the reason why that it's important, or it was important before we got statistical software, is that if you look at the PDF of a normal distribution, okay, so we'll go back to the standard one here. Down there's the PDF. And the general way that we calculate probability for continuous distributions is that we take the integral from point A to point B of that PDF. The problem is that you cannot integrate that PDF using standard methods that you learn in calculus. You can try it out if you want, but if you try to integrate that thing, you're going to come into, you're going to have some trouble, okay? So there's the e raised to the negative stuff, and you sort of keep going. And so it's, in a sense, it's non-integrable by sort of standard methods. And so you can integrate it numerically. So there are numerical integration procedures that you may or may not know. Probably not if you've not taken an advanced math course. But there are ways around it with software. But the normal distribution was of interest way before computers were existed or were easy to work with. And so what happened is that every distribution that you worked with would force you to do these really tedious calculations to try to work with the normal distribution. So there would be different calculations for a normal distribution with mean 50, standard deviation 5, and yet even different ones with a normal distribution of 50, mean of 50, standard deviation of 15. There's an infinite number of possibilities. But if I could take that regular distribution and turn it into a standard normal one, I essentially could do the same calculation for any distribution with this one distribution. So if I solve the problem for the standard normal distribution, then in a sense I've solved it for all of the normal distributions. And the reason, or the sort of tool that we can use to change any normal distribution into a standard normal one, is called a z-score. And so you may have heard of a z-score before. It's a very popular term in any sort of statistics course. And it's simple enough. You take x, and x could be a random variable. It could be like a whole distribution, or it could be an actual number. You subtract away the mean, and then you divide by the standard deviation. And in doing so, you've taken a normal distribution with arbitrary mean and standard deviation, and you've turned it into a point from a normal distribution with mean 0, standard deviation 1, the standard normal distribution. And so before they had computers, and people even teach it now there's such a thing called the standard normal table of distributions. And so people use these tables of distributions, not distributions, normal probabilities. And so they used these tables. In fact, your book has these tables at the end of it. So I think it's in Appendix A3. But if you go to the back of the book, you'll see tables of normal probabilities, and people still use these today. And what you do is you find a z-score, and then if you look at that standard normal table, then you can find probabilities using these z-scores. Fortunately for us, we have Minitab, and I'm not going to force you to use tables. So we've rendered this with computing power. We've rendered all this kind of stuff useless, or mostly useless, for what we're doing in the course right now. But it's still important. It's still important to get some practice with z-scores because they come up a lot later on in the course. So you have 2 your turns to end this video. The first your turn wants you to calculate z-scores. So I give you a normal distribution with mean 25, and we'll say here variance. So variance 5. And I want you to find z-scores for the following points. Okay, so remember that second number is actually sigma squared, not just sigma. Okay, so find those points, find the z-scores for each of those points. And then next, I give you, strike that. This should be mean 25, standard deviation 5. So treat this as a standard deviation, not a variance. Okay? And so again, treat this as a standard deviation, not variance. I want you to find the following probabilities. For this, you just need to use Minitab. So go to Minitab and choose the normal distribution, and then do sort of like you've done for all of the different distributions that we've worked with to find these probabilities. Okay, so I'll see you next time.